Jai Hind, ladies and gentlemen. Very warm greetings of the day and a hearty welcome to each one of you for this video presentation. The second video on UPRT covering various causes of upset conditions is being presented by Aviation Safety India for refreshing your knowledge and avoidance of accidents due to upset conditions. So here we go. First of all, we shall have a look at the objectives of upset recovery training. The objective of upset recovery training are to increase the pilot's ability to recognize and avoid upset situations, improve the pilot's ability to recover control if avoidance is not successful. Now we shall discuss causes of airplane upset. First of all, it may be environmentally induced, systems-anomalies induced, pilot induced, or a combination of all three above. Now we shall discuss the environmentally induced factors. First one is turbulence, then clear air turbulence, mountain wave, wind shear, thunderstorms, microbursts, wake turbulence, airplane icing. First, we shall discuss turbulence. Now, turbulence is categorized by a large variation in an air current or a short distance. It is mainly caused by jet streams, convective currents, obstructions to wind flow, and wind shear. Knowledge of the various types of turbulence assists in avoiding it and also the potential for an airplane upset. Clear air turbulence is defined as high level turbulence as it is normally above 15,000 above mean sea level. It is not associated with cumuliform cloudiness and thunderstorms. Clear air turbulence is categorized by marked changes in pressure, temperature, wind direction, and wind velocity. Now we will discuss mountain wave turbulence. Mountains are the greatest obstruction to wind flow. Therefore, this type of turbulence is classified as mechanical. Rotor or lenticular clouds or mountains are a sure sign of mountain wave turbulence, but sometimes the air may be too dry to show these clouds. Severe turbulence can be expected in mountainous areas if the perpendicular wind component exceeds 50 kilonewton. Now we shall discuss wind shear. Wind variations at low altitude are recognized as a serious hazard to airplane during takeoff and approach. These variations can be caused by many differing meteorological conditions. It can be topographical, temperature inversions, sea breezes, and frontal systems. Also, strong surface winds, thunderstorms, microbursts. Thunderstorms and microbursts are the two most violent forms of wind change. Let's now discuss thunderstorms. There are two basic types of thunderstorms: air mass thunderstorms, frontal thunderstorms. Air mass thunderstorms are then randomly distributed in unstable air. Heated air rises to form cumulus clouds, and the clouds develop in three stages: cumulus stage, mature stage, and dissipating stage. The gust front produced by the downflow and outrush of rain-cooled air can produce very turbulent air conditions. Frontal thunderstorms are associated with weather system, line fronts, converging winds, and troughs aloft. Frontal thunderstorms form in squall lines, last for several hours, generate heavy rain and possibly hail, and produce strong gusty winds and possibly tornadoes. The downdraft of a typical frontal thunderstorm is about 1 to 5 miles in diameter. Resultant outflow may produce large changes in wind speed. Look at the microburst. Microbursts can occur during convective weather conditions. 5% of all thunderstorms produce microbursts. Downdrafts are a few hundred to 3,000 feet across. Now we'll talk about wake turbulence. Wake turbulence is the leading cause of airplane upsets that were environmentally induced. A pair of counter-rotating vortices is shed from an airplane wing, thus causing turbulence in the airplane's wake. The turbulence, strength of the turbulence is a function of airplane weight, wingspan, and speed. Vortices descend at an initial rate of 300 to 500 feet per minute for about 30 seconds. The descent rate decreases and eventually approaches zero at 500 to 900 feet below the flight path. Maintaining a vertical separation of at least 1000 feet below the flight path is generally considered safe. Pilots have likened a wake turbulence encounter to be like hitting a wall. Now we shall discuss airplane icing. Large degradation of airplane performance can result from the surface roughness of an extremely small amount of ice contamination. The handling characteristics and maximum lift capability of the aircraft can be adversely affected. Now let's have a look at the systems anomalies induced airplane upsets. This can be due to the flight instruments, auto-flight systems, flight control, and other anomalies. In spite of improved airplane design, intensified training programs, and improved reliability, this system failure can take place. And some of these failures can lead to an airplane upset. Most failures are survivable if the flight crew makes correct responses. Now we'll discuss how flight instruments can lead to upset conditions. Instrument failures are infrequent, but they do occur. Airplane certification requires that the pilots have the minimum information needed to safely control the airplane in the event of instrument failure. However, several accidents point out that pilots are not always able to take timely corrective action. This can result in an upset situation. Now the auto flight systems which include autopilot, autothrottles, and all related systems that perform flight management and guidance. These systems integrate information from a variety of other aircraft systems. The pilots have tended to develop a great deal of confidence in the systems, which has led to complacency in some cases. Although auto-flight systems are quite reliable, failures do occur. These failures have led to airplane upsets and accidents. Flap asymmetry, spoiler problems, and other flight control anomalies are addressed in airplane operations manual. Flight control and other anomalies. Airplane certification requirements ensure that pilots have sufficient information, are trained to handle these critical failures. However, it is the unexpected then that can cause problems, particularly during critical phases of the flight. Now we shall discuss pilot-induced airplane upsets. Sensory inputs of the pilots can be misleading, especially when pilot cannot see the horizon. Inattention and distraction from primary cockpit duties and vertigo or spatial disorientation have also led to airplane upsets. Improper use of airplane automation is also one of the factors. Next, we'll talk about instrument cross-check. Instrument misinterpretation or a slow cross-check can lead to an airplane upset. Many minor upsets can be traced to an improper instrument cross-check. In addition to a good instrument cross-check and proper interpretation, it is necessary for the pilots to make the correct adjustments to pitch, bank, and power in order to control the airplane. Inattention and distraction from primary cockpit duties also have led to airplane upsets. Inattention, distraction, and neglecting to monitor the airplane performance can lead to extreme deviation from the normal flight envelope. Neglecting to monitor all the instruments or fixating on a certain instrument can lead to performance deviations. Distractions can be very subtle, such as warning or caution lights illuminating during critical phases of flight. Many airplane upsets occur while the pilot is engaged in some task that takes his attention away from the flight instruments. Controlling the airplane first should always be the guiding principle for the pilots. Now we shall discuss vertigo or spatial disorientation. Spatial disorientation has been a major factor in many airplane upset accidents. The definition of spatial disorientation is the inability to correctly orientate oneself with respect to the Earth's surface. We are all susceptible to sensory illusions. Pilots who perceive a conflict between bodily senses and the flight instruments are unable to resolve conflict or spatially disorientated. Allowed to continue, spatial disorientation will lead to airplane upset. Attention to flight instruments and a good cross-check are keys to remaining spatially orientated. Now we shall discuss improper use of airplane automation. The advancement of technology has enabled flight directors, autopilots, autothrottles, and flight management systems. When used properly, this technology contributes to flight safety and reduces crew workload. Complacent and improper use of these systems is a major concern. These systems can and do fail, leading to airplane upsets and accidents. Now we shall discuss swept wing airplane fundamentals for pilots. First, we shall discuss flight dynamics, then energy states, load factors, aerodynamic flight envelope, and aerodynamics in general. First, flight dynamics. In understanding the flight dynamics of a large swept wing transport airplane, it is important to first understand what causes the forces and moments acting on the airplane and then move to what kind of motion these forces cause. With this background, we can gain an understanding of how a pilot can control these forces and moments in order to direct the flight path. Newton's first law states that an object at rest will tend to stay at rest and, and an object in motion will tend to stay in motion in a straight line unless acted on by an external force. If an airplane in motion is to deviate from a straight line, there must be a force or a combination of forces imposed to achieve the desired trajectory. The generation of forces requires energy, which for discussion purposes can be called energy state. Now we shall discuss energy state of the aircraft. The term energy state describes how much of each kind of energy the airplane has available at any given time. Pilots who understand the airplane energy state will be in a position to know instantly what option they may have to maneuver their airplane. The three sources of energy available to the pilot are kinetic energy, which increases with increasing speed, potential energy, which is approximately proportional to your altitude, chemical energy, that is fuel available in the tanks. During maneuvering, these three types of energy can be traded, usually at the cost of additional drag. The relationship are airspeed can be traded for altitude and altitude can be traded for airspeed. Stored energy can be traded for either altitude or airspeed. Modern high-performance jet air transport airplanes have low drag characteristics in cruise configuration. Therefore, the pilot needs to exercise considerable judgment in making very large energy trades. A clean airplane operating near its limits can easily go from the low speed boundary to the high speed boundary very quickly. The process of controlling forces to change accelerations and produce a new energy state takes time. The longer time required by large airplanes requires that the pilot plan ahead that much more to achieve the final desired energy state. The objective is to manage energy so that the kinetic energy stays between limits that are stall and placards. The potential energy stays within limits that are terrain to buffet altitude, and chemical energy stays above certain thresholds that are not running out of fuel. Now we shall discuss the load factors. Newton's second law, force is equal to mass into acceleration, is the basis for discussing airplane load factors. Since the airplane has mass, if it is being accelerated, there must be force acting on it. Conversely, if there is a force acting on an airplane, it will accelerate. Acceleration refers to a change in either magnitude or direction of the velocity. It is convenient to refer to acceleration in terms of gravity, which is called g. The load factor expressed in g is typically discussed in terms of components related to the principal axis of the airplane. Load factors can be longitudinal, lateral, or vertical. In level flight, the vertical load factor is 1 time the acceleration due to gravity, that is 1 g. In a pull-up, the load factor is above 1 g and the flight path is curved. In a sustained vertical climb along a straight line, the thrust must be greater than the weight and drag. The wing and the load factor perpendicular to the airplane floor must be 0. Anything but 0 will produce a curved flight path. Acceleration is a result of the sum of all forces acting on the airplane. One of these forces is always gravity, and gravity always produces an acceleration vector directed toward the center of the earth. Aerodynamic forces are produced as a result of the orientation and magnitude of the velocity vector relative to the airplane, which are reduced into angles of attack and side slip. It is the direction and speed of the airplane through the air that results in an aerodynamic force. Aerodynamic flight envelope. Current jet transport airplanes are certificated to withstand normal vertical load factors from -1 g to plus 2.5 g in the cruise configuration. In addition to the strength of the structure, the handling qualities are demonstrated to be safe within these limits of load factors. The pilot should be able to maneuver safely to and from these load factors at these speeds without needing exceptional strength or skill. In conclusion, airplane upsets are environmentally induced, system anomalies induced, and pilots induced, which have led to a number of serious incidents or accidents. The pilots must be aware of the cause of upset conditions of the aircraft so that they can prevent or recover from the upset condition in a competent and effective manner. Sensory inputs can be misleading and may lead to airplane upset. Inattention, distraction, vertigo, spatial disorientation, improper use of automation instruments, misinterpretation and slow cross-check, and fixation have the potential of causing upset conditions. Pilots must understand flight dynamics and load factors. It is essential to remember that the first priority of the pilots must be to keep the airplane under control, and they had to be alert, vigilant, and situationally aware, particularly during critical phases of the flight to prevent any airplane upset. Thank you very much, ladies and gentlemen, for your time and kind attention. Hope you found this video useful and are better informed about various causes of upset conditions. Wishing you all very happy and safe flying and many happy landings. Jai Hind.